Okay, we're continuing with Chapter 7 in the trigonometry textbook. In this video, we're going to go through section 7.2, which is on the ambiguous case of the law of sines. So in this chapter, we're learning how to solve not just right triangles, which we learned how to solve using just regular trig functions in Chapter 2, but any kind of triangle. So any triangle that's not a right triangle is an oblique triangle. So we want to be able to solve oblique triangles, which include both acute and obtuse triangles. And we're doing this using trigonometry to develop the law of sines and the law of cosines. And we just, in the previous section, we were introduced to the law of sines. And what we saw, if we come back to section 1, was that the idea is you can't just solve any triangle. You have to have a minimum amount of information given to you about a triangle to think about solving it. Because if I gave you something like this is side length is 5, okay, and this angle is 15 degrees. And I said, solve this triangle. Well, there's no unique answer to this because there's not enough constraints. This triangle isn't fully constrained. I can change this angle, and then that would change this side length and this side length. So there's in this case, there's an infinite number of triangles that would have this side length of 5 and this angle of 15. There's an infinite number of answers to this question here if I said solve this triangle. Because what you're trying to do when you say solve a triangle, you're trying to specify what would this side length be, what would this side length be, what would this angle be in this angle. Well, again, there's an infinite number of answers to that. And so when we're going to think about solving a triangle, we're thinking about, have you been given a minimum amount of information to where the triangle is fully constrained? So in the sense that, yeah, you might not know certain side lengths and angles, but those angles are fully constrained to where there's only one answer to what that angle or side length could be, and you want to find out what it is. Now, how do we know when a triangle is fully constrained when you have enough information? Well, you can kind of figure this out in a roundabout way from the congruence axioms. The congruence axioms from geometry is where you're comparing two triangles to see if they're congruent. So like, for example, side, angle, side. If you can show that two sides, corresponding sides of a triangle, and one corresponding angle are the same, then those two triangles must be congruent. So that means all of the corresponding side lengths and angles must be the same if you can just show this. Well, we can look at that from another perspective. Like this, so there was 3 congruence axioms: side, angle, side, angle, side, side, side. Well, we can view this from another perspective in the sense that if someone gives you a triangle and they give you 2 side lengths and an angle that's included between those 2 side lengths, then what you can think about is that in a similar way to how that would mean that 2 triangles are congruent, you can think about the triangle that you're given is fully constrained at that point. You can, and that means you can think about solving it because, okay, so we've got this side length, and let's see. Well, let me do this. So this side length, and let's say this side length is 9, and then we knew this angle was 12 degrees. So there's side, angle, side. Well, in that case, now, so okay, A, B, C. So that means this side length would be B. Okay, so in that case, this means that side length B is fixed now. There's one unique answer to this, and same with angle A and same with angle C. So we can think about solving it, right? Okay, and so with that, because that's what we're trying to do in this section. We're trying to use trigonometry in this chapter. We're trying to use trigonometry to come up with some relations to be able to solve any kind of triangle, not just right triangles. And so one of the first things we do is we think about, okay, well, what are the scenarios where we can actually consider solving the triangle to where it's not, you can't give a unique answer to what the triangle will be. And so what that's based on is those requirements are based on the 3 congruence axioms. If you've got 2 sides and an angle included between the 2 sides, 2 angles and a side included between the 2 angles, or 3 side lengths, then the triangle is fully constrained, and you can think about solving for the unique values of the unknown values. Now, they point out, though, that side, angle, if you have a side length and 2 angles, but the side is not included between the 2 angles, that's like an offshoot of angle, side, angle, because with A plus B plus C equals 180, you can automatically solve for the third angle and then just make this angle side angle, right? You could just choose the two angles that sandwich that side length. So this is like just an extension of angle side angle. Okay. Now, however, what we saw was that there is, so okay, we want to look at these three scenarios here and see, okay, if we have this amount of this information, how can we solve the triangle then for the rest of the constrained values? But there is a case where that if you have a side and an angle not included between the two sides, okay, well, this isn't one of the congruence axioms. So that means that the triangle is not fully constrained in this case. So let me draw this. Okay, so you've got a side length, and an angle that's not included between those two sides. Okay, this is not one of the congruence axioms. So that means that this triangle is ambiguous in terms of, you know, that there's this. So if this is A, B, C, so this would be lowercase a. So that means that you could potentially vary side length A or angle B. It's not fully constrained. However, this is a special case to where there's not an infinite number of possibilities here. It is ambiguous, but it's not like the more typical situation of if you don't have a congruence axiom satisfied, there's an infinite number of possibilities, so it makes no sense to solve it. Like if you were given the three angles, you knew the three angles. Well, this is like you can make similar triangles of any size that all have the same three angles, right? I could scale this triangle up and down, right? So if you fix these three angles, but again, you can, I'm not changing the three angles, but there's an infinite number of possibilities for these lengths. So you can't solve the triangle. Okay, but in a case like this, it actually ends up being, well, what happens is there's only a few possibilities. Like the worst case scenario, the most ambiguous it could get is that like one of the side lengths could be there could be two different triangles that would satisfy the initial conditions. That's the worst case scenario. Sometimes it works out to where this actually ends up being fully constrained. But worst case scenario, you're going to be given a side and an angle not included between the sides, and there's two triangles that satisfy that condition. And so what we do is, instead of just ignoring this case, we call it the ambiguous case of the law of sines, and a proper final answer would be you just specify what the two triangles could be. Right? So we might say side length A could be this or it could be this. Like you just specify what the two triangles can be. So that's how you do it. Okay, and so that's why when you come here, they list out the four cases that we want to think about solving triangles. This first case it's a fully constrained triangle, angle side angle or side angle angle. We used the law of sines for this. Okay, now case 3 and case 4, it's still fully constrained, side angle side. So there's one unique answer for everything from the beginning. We're going to use the law of cosines to solve these. And now, but case 2 is this ambiguous case. This case here, we're going to use the law of sines for this case. And you might say, well, what about an ambiguous case for the law of cosines? There's no ambiguous. That doesn't come up with the law of cosines. It's just this one scenario, side angle. You have two side lengths and an angle not included between the two sides. In that situation, we use the law of sines and then consider the potential ambiguities. Now, what was kind of confusing is that in this opening section, all of the example problems they give in the opening section within the not at the end of the section, but like whenever we went through this section of the textbook, we looked at the example problems they gave and worked out. We never used the ambiguous case at all. We only used case 1. And that made sense because in section 2, what we're doing in this video is we're going to go over this ambiguous case. So I was assuming that they wouldn't work in the example problems at the end of section 1. They wouldn't have any cases involving the ambiguous case, but they actually did. For example, here was an example problem we worked at the end of this section 1, and we needed to find this angle here formed between the gears. So you have this triangle connecting the centers of these gears, and you know these two side lengths because you can add the radius of the corresponding gears, and you know this angle, and so that's a side, and an angle not included between those sides. And so this is when we had to use the ambiguous case here. And so I think what they're doing is that this is what they're going for. So for all the problems we worked at the end of this section with the ambiguous case, we were able to consider the potential answers, which for when solving triangles, it's nice because you can eliminate, the angle can't be negative, right? And it can't be greater than 360. So it's going to be at worst one of two angles to consider. And we were able to look at the problem and figure out what the angle had to be between the two possibilities. Like we knew if for example, if the angle was, if we solve for this angle here, if this was an obtuse angle like 135 or something, well then this had to be acute. But that didn't make any sense because that would mean that this is going to be one of the shorter sides, and so we could figure out that there's no way this could be an obtuse angle. It had to be the acute angle. Okay, but what they're going for in this section is they want to look at it. They want to look at it from a complete general perspective, almost like a design perspective. It's like if you were designing, you had no idea what the triangle was going to be, then how can we really get a good look at how what the ambiguous case is what's going on there? So they want to really look at the big picture of the ambiguous case, which is, it's going to be really interesting to be able to understand how triangles work and just understand the ambiguous case and just solving triangles as well. And again, but even like from a design case, if you were you had no idea where these gears were going to be, so it was completely open-ended, but you had two side lengths at an angle, well, then you have no idea what the constraints are going to be. You have no clue what one side length might be relative to another. So in that case, what do? Well, you have to be able to say, okay, here are the possible triangles, and put the two possible triangles, and then decide from there. Because again, it's not so ambiguous to where you could have an infinite number of possibilities. It's worst case scenario we're going to see with the ambiguous case is that there's two possible triangles, two separate triangles that could result. If you're given two side lengths and an angle not included between the two sides, worst case scenario is there's two triangles that satisfy that. That's worst case scenario. But we're going to see actually it still could be the case that there's only one triangle that satisfies the criteria, or even sometimes there's no triangles. Now, does that mean that in this case here that there was only one triangle that satisfied the criteria? Well, I think in this case it actually turned out to be true. And what I mean by that is there was two possibilities for angle C. And then when we added the obtuse possibility to 38, which was fixed, it was greater than 180. So that triangle couldn't be a possibility anyway. But for this problem, we solved for angle C, and there was two possibilities. And then when we took the obtuse possibility and added it to 18, it was less than 180. So in that case, there's actually two. So we know we started with two side lengths and an angle, not included between the side lengths. So technically, there's two triangles from that perspective. There were two triangles that satisfied the criteria. For the previous case with the gears, there was only one. In this case, there were two. However, we could still, in this case, eliminate the possibility of one of the triangles because there's no way that we could have, like, this angle could be obtuse. And if in that case, this would be a really small angle, it wouldn't make any sense. Okay, so we didn't even look at the other possible triangle, but what we're doing in this section is we're thinking about, okay, it's kind of like from a design standpoint. Let's state all the answers, potential answers. Like, okay, we start with these constraints. So here are the two triangles we could have, and like that's the final answer. It's like completely open-ended. Okay. Okay. Let's take a look. We have used the law of sines to solve triangles involving case 1, the side angle or angle side angle condition, the nice case, non-ambiguous case. But if we are given the lengths of two sides and the angle opposite one of them, then we have the side-side angle case, the ambiguous case of the law of sines. And in that scenario, there's three possibilities. You could have, it could be the case that there's no triangle that's possible. So, okay, imagine you're given, so the way they present this section is kind of confusing. So, okay, we're looking at this, imagine, so this is completely open-ended in that we don't have a picture of some gears. We don't have any information except, like if we come here, okay, this first example, all they gave us is that we've got one angle and two side lengths of a triangle. That's all they gave us. That is it. It's completely open-ended, right? And they're telling us to solve this triangle. So when we would see this here, the first thing that would come to mind is, okay, we've got two side lengths and an angle. Maybe the angle is sandwiched between the two side lengths. That side angle side. Law of cosines is nice and straightforward. There's no ambiguity. Can we use the law of cosines here? We haven't learned the law of cosines yet, but once you learn it, that's what you would think. But then we look at the specifics of this, and based on the triangle notation, what we realize is that the two side lengths aren't sandwiched between the angle. So in that case, we've got the side. We know we have the side angle condition. And so we know this is the ambiguous case of the law of sines. Okay? And so with that, what they're telling us here is that now that we know that, with these constraints, because these constraints can't change, that's the whole point, right? That these constraints are fixed. In that case, there's going to be one of three scenarios is going to come out of that. Either no triangle is going to be possible with those constraints, no triangle. One triangle is possible. So in that case, it's actually kind of nice. It kind of corresponds to the congruence cases. There's only one unique triangle that works. Great. Or there might be two triangles that correspond that work with those constraints. Okay, and so that's as ambiguous as the ambiguous case of the law of sines gets. The worst case scenario of ambiguity is that there's two triangles that satisfy the criteria. So what I mean is that if you were asked to solve a triangle and it's the ambiguous case of the law of sines, if it's the one triangle case, then just draw that triangle and give the side lengths and angles, and that's your answer. If it's the no triangle case, then just write there's no solution here. There's no triangle that works for that satisfies this. If it's the two triangle case, then your final answer is going to be two separate triangles with all of their side lengths and angles. And you say final answer is one of these two triangles. Either of these two triangles satisfy the initial conditions given. Okay, and that's the worst case scenario. For all of the other, using the law of sines for any of the other cases in the law of cosines, you can have one and only one triangle. This is the worst case ambiguity where you have two triangles with the ambiguous case of the law of sines. Okay, so the goal of this section is, the idea is we're not given, what we want to be able to do is, we're just given a completely open-ended case of just here's some side lengths and an angle, and from there can we analyze what are all of the possibilities that come out of this, right? Again, completely open-ended. We don't have some gears and we can kind of see what's not possible and what is possible. No, let's just analyze this from a complete general standpoint, okay? And so the way it works is, I mean, this is actually not as hard to do as you might think. So we're going to go through this here. It's easier than you might think it is. But these are the 6 cases. There's only 6 possibilities of anything. When you've got the side angle condition, you realize you've got two side lengths and the angle is not sandwiched between those two side lengths. There's 6 scenarios. And you can see the number of possible triangles. You could have none. No, it's not possible. There's only one triangle, not possible, or 2 triangles. So there's actually only one specific case where you have 2 triangles or come out of it. Everything else is either one triangle or no triangles. Okay, so the first thing to notice is that, notice how they said that if we are given the lengths of the side angle condition is the case where we've got the lengths of 2 sides and the angle opposite one of them. That's important to notice, okay? What that means is that you have, so if we come here, you have an angle, okay? So we have one angle. So there's the angle. But with the side angle condition, 100% we're going to know the side length opposite of that angle, 100% every time. You might say, well, what do you mean? Why couldn't, what if the side length happens to be this side length? Well, then in that case, we would have the side angle side condition. In that case, the angle would be sandwiched between the two side lengths. We don't have that. Because we know that the angle is not sandwiched between the side lengths, that means that one of those side lengths is going to be opposite the angle we know, 100%. Now, you might look at this and say, well, so we know side length B, and we know this other side length that they didn't draw in. We don't know this side length, but what if B is below angle A? Okay, well, it's important for you to realize this as well, that this is just a matter of the way, your perspective. Okay, you can take, okay, so here's, copied this. You can take any orientation. It could look completely different from this. You're allowed to flip this into or out of the page, rotate it, flip it horizontally, vertically, rotate it in the page, whatever you want, as long as you're not changing the side length or the angle. And you can think about it, you can absolutely do all of those. You can reorient something without changing it, the size of it, the angles of the side lengths. You could put it into this position with no problem, to where the side length we don't know is horizontal left to right, and the side length on the other side of the angle that we know is right above it, like this. And then you got the side length opposite like that. So like I'm saying I could take this, and without changing this side length or this angle, I can do whatever I want to it. I'm not changing the side length or the angle. I'm not changing anything. I just flipped it vertically. I didn't change anything about the nature of what I'm working with in terms of the side lengths that were given to me and the angle. So you can reorient and put it into this position. It's important for you to realize that, because it's from this perspective that we're going to be analyzing these cases. Okay? And again, I'm going to say it again. If you have the case where you've got the side angle condition, which means you've got two side lengths, and with one of those side lengths being in side length opposite angle, then you're able to you can put whatever your circumstance is into this position to analyze these cases, to see what case you're dealing with. Okay, now I don't want to just go through this table, just read through it. What I think will be better is okay, we've got this example 1 over here. Let me bring the given parameters from example 1 so you can see it. Okay, so the idea is that we're given something like this. In the open-ended case, we're just given these 3 parameters here. We're given an angle and 2 side lengths, and we can see based on the notation, the triangle notation, that one of these side lengths is opposite from the angle we're given. So we know we have the side angle case. And now we're just asked to solve the triangle. Okay, so that's the idea. So what's the simplest way for us to analyze this so we can quickly and easily figure out exactly what case we're dealing with? And I know I haven't explained the cases to you yet, but it'll make it a lot easier if we just kind of learn this all at the same, work this problem and learn this all at once. To me, it's confusing if we just try and read through this. So, okay, the first thing that you need to realize is that, and the book purposely does this, is that, so like we've got angle B here, side length B here, but side length A here, but the letters here don't match up in terms of what angle they're actually corresponding to. And the book does that on purpose. So we really need to understand not the letter here, like what like the letter B, but what angle in this setup here, right? It's all kind of rooted in this starting orientation. What angle is this corresponding to? Because like angle B here and angle B here aren't the same angle as far as this setup here. Again, the general setup is we start with, we can put the side length we don't know horizontal, so this side length could be anything. Then we pivot a line here that's at the angle that we are given, so the orientation of this line is fixed, and this side length is fixed because we know that side length. And then over here, they didn't draw it, but we've got a side length that the length of it is fixed. But it can pivot because this angle C we didn't specify, and also this angle over here, what they're calling angle B, that's going to depend on the final triangle. We didn't specify that either, right? So the only parameters that are fixed are this angle, the length of this line, and the length of this line. But these are free to vary. Angle C, this length, and this angle. Okay, so now when you look through all the cases, though, it looks like the side length A is allowed to vary, but it's really not. They're just varying it for the sake of to illustrate the cases. The idea is if A is fixed, and if it meets this constraint where like A is less than B, then you know you're dealing with potentially this case. But it's actually not. It's actually A is not variable. Okay, so now, so we want to get away from looking at letters and thinking about what angle position and side length position this corresponds to. So the general idea is when we start from this general setup, if we're wanting to analyze, we're looking at this, we can draw our horizontal line, and then we can add in this line here, and we know that this angle is going to be the one angle we know that we're given to start with. So that's going to be angle B here, which corresponds to angle A here. That's the given. It's side angle. That's the angle we know. So you can start by just drawing a horizontal line to analyze this. Draw a horizontal line, then you have this line here, and you could kind of just eyeball what the angle is. So 55 degrees, 40 minutes. So that's about 45 degrees. Go a little bit more and just put a line here at about 55 degrees. There we go. Okay, and we could put B here for this notation, but it gets confusing because B corresponds to A here, right? Okay, now the next thing you're going to do is take a look at angle B and see, okay, is angle B acute or obtuse? Because that's what this is referring to, is the angle you know, side angle, is the angle you know acute or obtuse. In this case, it's acute, so we know we're not dealing with these two cases here. It's going to be one of these four cases that we're dealing with, okay? Now, the next thing you want to do, and my recommendation is they included in here, they compare, so what they're doing is, for these criteria, let's ignore sine of B, the signs of B for now, but they're for each of these criteria, like you see if the angle is acute or obtuse, but they're also comparing the two side lengths, the two side lengths that you're given, and to each other, but also to the height of the triangle, where there's three different heights of a triangle that you can draw, but coming from this vertex C, to me that's confusing. We're going to ignore. You're not going to think about the height. If you're dealing with the ambiguous case of the law of sines, you don't have to think about a height. I'm going to give you a method to where you don't have to think about it. So forget the height. All we're going to do, the next thing we're going to do, is compare the two side lengths we know. But now we're not comparing. I'm not going to say we're comparing side A to B, because remember, the letters don't meet. It's more about the positions than the letters. We're comparing the length of the adjacent side to the length of the opposite side. So in this case, the opposite side is side B, adjacent side A, but in this table, the opposite side is side A, adjacent side B. Okay, but forget about the letters. What do we see here? We see that the opposite side is shorter than the adjacent side. That's what we see here. Okay, now, so we've narrowed it down from the acute to these four cases of the acute angle, but now we can narrow it down even further, because here's a case where the opposite side is greater than or equal to the adjacent side, the length. So this case is out. So now we're down to three cases. Okay, what's next? The next thing we're going to do is we're going to kind of eyeball it again. So we can see that the adjacent side is actually pretty long. So maybe we can, if you can adjust the length of this, make it a little bit longer, the adjacent side. And now we know the opposite side is going to be here, and we know it's going to be on like a hinge here, because this angle is variable. The length is going to be fixed, because we're given it's going to be 8.94, but it's going to be on like a hinge here, right? But let's think about the length, though. So 8 is like 1/3 of 25, right? 8 times 3 is 24. So it's about 1/3 of this length. So a half, about 1/3, okay? So now try and keep that length constant, but we can vary the angle, right? But let's try and keep the length constant. The length is fixed. But what do we notice here? If we can't change that length, we can, right? what do we notice? We can't make a triangle. Why not? What happened? Well, because it's a relation between this angle combined with the length of this side is too big. To make this work, we need to make this angle shorter and or this side length shorter. But as it sits, we can't make a triangle here. And that would correspond to, we were left with 3 cases. There's only one case where you can't make a triangle. 0 triangles that was left of these 3 cases. That's this case. So, but does that mean we have this case? Well, just eyeballing it, it seems like we do. But I didn't officially prove that. I mean, I didn't draw this angle precisely. I didn't measure these lengths precisely. It looks like it is. That's going to be the case. But we didn't officially prove it. So how can you officially know if, okay, we do in fact have the case where the not possible case of the not possible acute angle case. There's only 2 not possible cases, one for the acute angle, one for the obtuse angle. We've got the acute angle. So how do we know for sure that we have the acute angle not possible case? Well, that's what they're talking about. That's what these sign relations are talking about. And they're saying the sine of angle B. So again, it's not this angle B, it's if you completed the triangle, the sine of the angle between this side length A and side length C over here would be opposite side length B, right? But we don't even have an angle. Like, how do they know we don't even have an angle here? And not only just that, but like, how come they're using sine of B for all of these? Why not sine of C? Like, why is the sine of angle B such a descriptive factor of these cases? Well, because think about it. If we apply, let's see. This is angle. This is A, so that means angle A is going to be over here. This is going to be angle C, and then length B is over here. We can right now. Let's imagine we have a triangle. Let's do the law of sines. Okay, so what are we going to do? Well, okay, we've got angle B and side length B, so absolutely, let's go ahead and say sine of B over B, all right, is equal to. So now, okay, do we want to use angle C? Maybe, but we don't have side length C. We have side length A, so let's do this. All right, one equation, one unknown. We can solve for sine of A. You're going to have A sine of B. So there you go. We're going to have sine of A is equal, and we're going to get a number because we know A, we know angle B, and we know sine length B. Well, what's going to happen in this case, what we're going to end up getting is sine of, note that sine of B in this case is the same thing as sine of A as far as the position of A and B, right? We're talking about, these angles here, sine of B is referring to this angle over here. So what's going to happen, they're telling us, is that we're going to get sine of B is greater than 1. If we wrote all this out, you can see over here, if you come over here, they went through the law of sines. They got sine of A is approximately 2.318 this, right? It's greater than 1. So if we come back, it's greater than 1. Well, sine can't be greater than 1. Sine, the range of sine and cosine, right? You can't get a value greater than 1 or less than -1. So that's what's telling you that you're getting the not possible case. The triangle, you can't make the triangle. That's what it's telling you. Okay? And so that's how we could prove it officially. We did it unofficially, just kind of drawing a graph and taking a look at it. But now if we actually applied the law of sines and got sine of A is equal to some number greater than 1, now we know our angle is acute for sure, right? It's 55 degrees, whatever. We did the law of sines. We got that the sine of this angle is greater than 1. We know we've got the not possible case for the acute angle not possible case. All right. Now, what you can think about, though, is that for any of these cases, for any side angle case, it's always when you do the law of sines, it's the same setup every time, right? You're gonna get some, when you do the law of sines, you're gonna end up with the sine of this angle on this side is equal to something every time. And that's why for each of these cases, they're stating information about the sine of this angle over here. The angle connecting the opposite side to the angle you know to the side that you don't know, you didn't specify. You do the law of sines for every case of side angle, ambiguous case of law of sines. You do the law of sines, you're going to get something pertaining to sine of B, or the sine of this angle over here. In this case, it was sine of A. You see? Okay. Now, let's say we were given this same problem here, but we made side length B a little bit longer, because that would potentially help fix the problem, right? We had, here's A was pretty long. Okay, this was A, and this side length B over here was too short, right? So let's make it a little bit longer. And as we make it a little bit longer, we're going to be getting into another one of these cases, okay? So what we're going to do is we're going to make this longer, but it's still going to be shorter than side length A. Remember, the first criteria was we're sticking, we see, do we have the angle we're given, is it acute? So we're staying with the acute angle case, so we're not here, okay? The next thing is we analyzed is what's longer, the adjacent side or the side opposite the angle we have. Okay, for here we saw that the adjacent side was longer. So we're making this longer, but we're still going to keep this length shorter than A. Okay, but right here we still have the same case. You see, we're still in the no triangle possible case. So there's going to be some point, though, where we are actually able to make a triangle. So it's going to intersect out here. Now, what we want to do, though, is you could say, well, let's do it here. But the only thing is, remember, we're on an arc, because we're going to fix this at some length. We're given this side length. It's not like this is a variable side length, like this angle is variable. We're actually given this side length. It's going to be fixed. We're just analyzing the different cases. So let's say we were fixed at this length. Well, we could rotate this in an arc, and we could also have a triangle over here. So let's progress through this slowly. Let's make it to where this line extends, and throughout this entire arc, there's only one triangle possible. So that would be where, if you have a circular arc that this is fixed, and it just kisses this curve at one point, and then every other possibility, there's no triangle. Well, you can think about it. I'm not stating this officially, but that's going to be like a straight down case. Like if we dropped a perpendicular from this vertex, right? Now, I'm not stating it officially, but it seems like it's going to be straight down. Since this was horizontal, it seems like it's going to be straight down. So I'm not going to put the perpendicular yet, but okay, so it's straight down. And remember, this side length over here is completely variable, so we can just make it whatever length we want. So there's a triangle. So we've got side length B, angle C, side length C. Okay, now, if it was in fact the case that this line was just long enough, perfectly long, to where it kissed the curve at one point like that, then it is going to be perpendicular. Okay, this is going to be the right triangle case. But to know that officially, if we did the law of sines again, I don't know what this side length would be, but this would be a longer side length, right? If we did the law of sines again, what we're going to end up with is sine, and this is angle A, sine of A is equal to 1. That's what we're going to end up with. And that's what's going to tell us officially that this angle is 90. So that's how you know if this length is perfectly long enough to where it kisses this bottom line at just one point like that. It's going to be like a straight down line relative to the horizontal line, and it's going to be perpendicular because you're going to do the law of sines, you're going to get this. And we know if we take the inverse sine of both sides, inverse sine of 1 is, there's only one angle between, so right now we took inverse sine of both sides, right? So when we're doing the law of sines, I don't want to go too fast here. When we're doing the law of sines, we take the inverse sine of both sides. But now there's ambiguity, right? We just introduced this inverse sine, so we have to think about all of the possibilities here of all the angles that when you take their sine, you get 1. But fortunately, we're dealing with triangle angles, so it can't be a negative angle. It can't be an angle greater than 180. So it's just going to be an angle between 0 and 180. Well, the inverse sine of 1 is a special case where there's actually only one number between 0 and 180 degrees, where when you take its sine, you get 1. and that's 90 degrees. So that's how you know you have a 90-degree angle. And that's how you know you're dealing with this second case here, because the angle was an acute angle, and you found that the sine of B was equal to 1. So you know you're dealing with this case. You know that the opposite side length is equal to the height, if you want to think about the height. So if we want to actually think about the height, we started off where the opposite length was shorter than the adjacent length and shorter than the height. But then we kept extending the length of the opposite side length. And once it became equal to the height, we got this right triangle case. And now what we're going to do is let's bring in the second example in the section. They didn't give an example of the right triangle case within the section. Okay, so here's the second example. And so, okay, we're just given these parameters here. We've got two sides and an angle. Hopefully it's the side angle side case, but we can see one of these side lengths is opposite the given angle, so it's going to be the side angle case. So let's draw the horizontal. That's the side we don't know. And then we see we've got an acute angle that we're given, so we know we're not in these two cases here, the obtuse cases. All right, now let's go ahead and just draw the adjacent side approximately at that 55.3 degree angle. So that's about 45, so somewhere around there. Okay. Then, so that's going to be angle A. This would be C, B, and this is B. So this notation actually matches up with the table. But, okay, now the next thing we're going to do is we want to compare side length, the opposite side length we have to the adjacent side length. So opposite is 22.8 feet, adjacent is 24.9 feet. So opposite is less than the adjacent. So we're still in that, we're increasing the opposite side length. We just did a case where we started off with there was no solution. Then we got to the case where the opposite was just equal to the height. Now we've increased it a little bit more. It's still less than B. So A is still less than B. Or the opposite is still less than the adjacent. So we know we don't have this case because, right, A is greater than or equal to B. So we know, once again, we're dealing with one of these three cases. And so now, but, maybe this example 2 is a no solution case. Maybe it's a perpendicular case. Let's see if we can make an educated guess of what it's going to be. So, okay, B is 24.9 feet, and in this case, A is still less than B, but it's close to 24.9, right? It's just a little bit less. So we're here. That would be A is equal to B, just a little bit less this time. Okay, so now let's rotate. We can vary angle C. Let's try and keep the length constant of A constant. So, all right, there we go. We got a triangle. But now I guess let's keep rotating. No triangle, no triangle. Okay, there we go. We've got another triangle. So it seems like there's two potential triangles. There's two triangles that satisfy the criteria we're given, which of these last three cases here that are remaining, it suggests that we have this case, which again, there's two triangles that satisfy the criteria. So, okay, if that's the case, then they label, we have like two B's. This is B2, and this is B1. This is A. Okay, but we just did that informally, right? So let's check this to see if we have this case. Let's do an official check. So let's apply the law of sines. So you've got sine of A over A is equal to, and we're not going to say B2 or B1. Let's just put B. Okay. As far as checking the law of sines, checking to see what case we have, just put B, because we don't officially know what case we have. We just did that informally with a visual aid. Maybe I didn't measure it right and I was wrong, and it is the perpendicular case or the no solution case. So we're just going to put sine of B. Like right now, we're doing the law of sines right now. I drew this picture, but we're still doing it off of, we're like here right now. As I'm doing the law of sines, right? This is just an educated guess on what we have. Right now, we're really still at this stage. We don't know what we have. So, okay, over B. So if you plug all that in, what you're going to, and solve for sine of B, what you're going to get is, okay, and then if you take the inverse sine of both sides and solve for B, in this case, there's going to be two angles between 0 and 180 that satisfy this, the sine of those angles equals this. It's going to be 63.9 or 116.1. Okay, so now we know that we definitely have this case here. Because remember, we narrowed it down to, we had an acute angle, and then we knew that the opposite side was less than the adjacent side. So we were left with these three cases. Well, okay, we know we don't have either of these two cases because we got sine of B. It's not greater than 1 for sure, and it's not equal to 1. So we're left with this case here. And it makes sense that we got two possibilities, B2 and B1. So it matches up as well. Now, I believe that once you verify that you have an acute angle and the opposite side is less than the adjacent side, and you get two angles like this, I believe that once you do that, then it's official that you have two triangles and you can go forward from there. However, it's good practice to check. I don't think this will ever end up not checking out, but you can think about what you can do is you have an angle, right? And so this is B2 is going to be the obtuse angle, and B1 is going to be the acute angle. Well, what you can do is you can check, add 116.1 to angle A to 55.3. And if you do that, you get 171.4. And you're doing that because, like what they're saying here, A plus B2, it can't be greater than or equal to 180, or else that would mean, you have to have something less than 180 for, so angle, not angle C, but this angle here is greater than 0. It has to be to have a triangle, right? Now you can check that, but I believe that that's going to check out no matter what. But I guess it's good practice to check it. Okay. Now they say here the sine of B1 is going to be between 0 and 1, but so is the sine of B2. The sine of an obtuse angle is something between a positive number between 0 and 1, and so is an acute angle. So yeah, but that's how you know that you're dealing with this case 4 here. Okay, and so, but like what you would do next is you wouldn't, to actually complete the problem, you would actually draw these two separate triangles, put the angles, and then just go ahead and solve the triangles, both triangles using the law of sines, which will be easy because you've got, for each of the triangles, you've got two angles. So, okay, it would be, let's see, this triangle and then this outer triangle here, right? Not this inner, not this one, no, this outer one. And B2, this angle, this angle, this angle, that's angle A, and this side length, and this side length. So you can solve for the third angle. 3 angles and 2 side lengths, you're home free. And you just present both of these triangles as your final answer, the fully solved triangles. Okay, so here is the third example in this section. So we look at this and we see that we know an angle and 2 sides. We think, well, man, I hope that's side angle side, but it's not. We have one of the side lengths opposite the angle we're given. So it's this side angle case here. It's going to be one of these cases. Side angle, law of sines, ambiguous law of sines case. Okay, now the first thing we do is we look and see, do we have an acute or obtuse angle that we're given? Well, it's an acute angle, so we know it's not one of these cases. Okay, so let's draw a horizontal line here and put in a side length that's about at 45 degrees-ish, a little bit less. Okay, that's fine. Okay, now let's compare the lengths of the two sides we have. So in this case, the side opposite the angle is, and so this is going to be the adjacent. This is going to be B. Okay, so the side opposite the angle we have is greater in length than the adjacent side. So, okay, we were left with these 4 cases. this is actually nice because there's all three of these cases don't satisfy that criteria. All three of these cases, the opposite side length is less than the adjacent side length. Here, this case, if it's the opposite side length is greater than or equal to the adjacent side length, then you have this case. So we have this case here, which is nice. So we don't have to do any more analysis. We know we have this case. And so, yeah, they say sine of b is going to be between 0 and 1. So we can check that. And if we don't get this criteria, then we know something's wrong, but we're going to get this. Okay, so, I mean, we can go ahead and do that real quick. So b is, they're talking about c. So we do sine of c over c. And then we know sine of a, and we're given a as well. So we're given c, we're given angle a, we're given side length a, so we can solve for sine of c. And if you did the calculation, sine of c is approximately 0.4632. And there you go. It's between 0 and 1, so we're good. But now this is a little bit confusing because aren't we going to get two angles out of this? Huh. Okay, well, let's look at this graphically first. So we know that we're going to be greater than this length, and so this side is going to be greater in length than this side. So let's see, it's about, just comes out to about right there. Okay, so now this is a free angle. Well, no, coming out here. Okay, now we can obviously extend this length to wherever we want. Okay, so there's a triangle, but now could we keep rotating side A and make that work? Well, no, because, all right, you might think that we can, but remember, so, okay, we're out here, we're rotating. Remember, we cannot move this side length here is fixed in the horizontal position by the angle we're given, right? It's fixed by this angle. The orientation between this side and this side is fixed. The length we can vary, that's no problem. But if we kept rotating side A, then we can't make a triangle because we can't move this off of its position. So there's only one triangle here. Okay, so, but, all right, let's solve for C. Angle C. You get 27.6 degrees or 152.4 degrees. So what's going on here? Well, there's only one triangle because in this case, if you have these constraints where the opposite side length is greater than the adjacent side length with the acute angle, what's going to happen is, so let's take this obtuse angle and add it to what the angle we have, 43.5. Well, 135 plus 45 is 180. That's going to be greater than 180. So this is not possible. That's what's happening. This is, you can't make a triangle with this, having this angle and the angle we were given originally. That's the difference between with the case where we had two triangles. The obtuse angle actually worked. This angle doesn't work. So there's only one triangle where with the angle C being this angle. Okay, now what if you're given an angle and two side lengths, but the angle you're given is obtuse? It's the side angle case, but you have an obtuse angle. Okay, so we draw the horizontal line to start with. Now we can put in this side with whatever the angle is, but it's going to be obtuse, so it's going to be somewhere like over here, right? So we've got this, we're given this angle A, and this is side length, based on this notation, side length B, and then this would be angle C, side length C, angle B. Okay, so what would we typically do next? Well, we've got this side length, right? So next what we would do is we compare this side length, opposite angle A, to the adjacent side length. Well, okay, what you can see is that if this side length is less than or equal to this side length, no triangle is possible, right? I have to be able to get back to this line here where I can't change the orientation of this line, right? Because this angle is fixed. Angle A is fixed. I have to be able to get back to this line, but it can't just be a straight shot. Like if this length was equal to B, yeah, I got back to that line, but there's no triangle. But if it's just a little bit longer than side length B, then I can make a triangle. Right? If it's just the tiniest bit longer than side length B, I can make a triangle. But if this length, if length A is less than or equal to B, I can't. No triangle is possible. Okay, and so that's the idea. It's pretty straightforward when you have an obtuse angle in the side-side angle case. So here, if you did the law of sines, you can still do the law of sines with the no, it's not possible case. You're going to get the sine of B is greater than or equal to 1. And if you do it with the possible case, if you got something like this, right, you're going to get that you're going to get sine of B is something between 0 and 1, which, okay, but there's two possibilities, right, that comes out of that. You're going to get an acute, you're going to get B is equal to an acute or obtuse angle, but this is really clear to see. Angle A is obtuse. It's not possible to have two obtuse angles in a triangle, so 100% can't be the obtuse angle. And so there's your one unique triangle with B being the acute angle. Okay. Now, the last thing we want to take a look at, and this is actually pretty interesting, and this helps you to analyze the constraints between triangles. So it gives these three basic facts here. It says to help determine which situation applies. We've already really talked about this first one. It should be pretty clear now. For any angle theta of a triangle, the sine of the angle is going to be between 0 and 1 because, right, sine is positive in quadrant 1 and quadrant 2. Any angle of a triangle is going to be acute or obtuse. So you're going to have, no matter what the angle is, acute or obtuse angle, the sine of that angle is going to be something between 0 and 1. And it could be equal to 1 if it's a 90-degree angle. And that's what they say here. Sine theta is equal to 1. That's a 90-degree angle. Here, all they're talking about here, so sine of theta is equal to sine of 180 minus theta. They're just saying that you don't really need to memorize this. They're just pointing out here that when you get to, like, if you're taking the inverse sine of both sides and you're having to analyze the different angles that satisfy the criteria because you introduced the inverse trig function. Well, in general, we know that the way you do it is you find what the angle of the inverse trig function is based on the possible outputs of the inverse trig function. Then you think about, okay, what angle between 0 and 360 degrees satisfies this question here. So you typically you're going to get two angles. One angle, it might be acute, depends on what the inverse trig function is. It could be like inverse cosine goes from 0 to 180. You're going to get one angle between 0 and 360, and then there's going to be another angle between 0 and 360 that's going to like pair up with that. And then the final answer is like those two angles or any angle coterminal with those two angles is like satisfies the inverse trig function question, right? Or satisfies the trigonometric equation. Well, with sine, it's actually a special case to where if you actually if we're doing inverse sine of 1/2, then we put this into the inverse sine function into the calculator. You get an acute angle. To get the other angle, then just take 180 minus that angle, and you're going to get the other angle, and it's going to be an obtuse angle. So you don't have to memorize that. I mean, you could just, this is kind of, I think that you don't need to memorize this, but that's the idea, that it's like a special case when it comes to inverse sine, to where if you want to get that, you're always going to get out of the inverse trig function an acute angle. And then if you want to find the other angle that answers the inverse trig function question, you can go through the full thought process of analyzing the inverse sine function, or you could just say 180 minus that angle, boom, you got it. Because you know it's going to be in quadrant 2, and it's a result of that supplementary angles have the same sine value. Okay, now this third point is pretty interesting, and this is actually really helpful for analyzing triangles. So the smallest angle in a triangle is opposite the shortest side. The largest angle is opposite the longest side, and the middle valued angle is opposite the intermediate side, assuming you have a triangle that has different angles, different length sides and magnitude angles. And so, yeah, what they're saying is that, like, for example, if you have an obtuse triangle, okay, well, the angle of a triangle, what is it giving you? It's the amount of separation between the sides, right? So if the sides are separate, if it's a big angle, that means the sides are separated a good bit. That means it's gonna take a longer length line to connect these two ends, right? Which corresponds to that length corresponds to the side opposite the angle. So the larger the angle, the larger the side, the side length opposite that angle. And in general, that's how it's going to be. If you want to know what side is the longest side in a triangle, what side is the shortest side, what side's intermediate, look at the angle. If it's a really small angle, then opposite that small angle is going to be a really short side. And so that idea is really helpful in analyzing triangles. So if we come to this last example, it says, without using the law of sines, explain why, if you're given that A is 104 degrees, you're given this angle and these two side lengths. Why can that not be a valid triangle? Why is that? They're saying so we've got side angle, because this side is opposite this angle. So we've got side angle, ambiguous law of sines, with the obtuse, the angle we have being obtuse. They're saying that we don't even have to use the law of sines. We can just see by inspection that this is going to be the no solution case for the obtuse angle no solution case, just by inspection. So, okay, let's see. We've got, here's this side length, and then we've got, so there's 90 degrees, about 10 degrees. There's about 104 degrees, okay. Now, let's see. So now this side length here is the side opposite the angle we're given is shorter than this side length. Okay, so yeah, we can see visually why this is not going to work. But another way to think about it is that the 100, what they're saying is that the side length opposite the 104 degree angle is not the longest side in the triangle. So that would have to mean that there's another angle in the triangle that's bigger than 104 degrees. You can't have two obtuse angles in a triangle. It doesn't satisfy the three angles summing to 180 constraint. So that's another way of looking at the obtuse no solution case from the perspective of you can't have the longest side of a triangle has to correspond to be across from the largest angle.